to improve low-dimensional data visualization. Centroid-encoder maps training data through auto-encoder targeting mean of associated class. So just quickly, on the top here we have a visualization of digits per class in MNIST training dataset. Thanks to the autoencoder targeting mean of the centroid of the classes, we can see all the classes very nicely separated in their Voronoi cells. And here on the bottom, we can see visualization of the training data, where similarly to the original training set, the data is separated in their cells, but because it's test data, it's not, it was not trained for, you can see that the data also are spread into other cells. So today I'm reading Supervised Dimensionality Reduction and Visualization using Centroid-encoder. It's from 27 February 2020 preprint from Tomoji Ghosh, Michael Kirby from Colorado State University. Abstract is following. Visualizing high-dimensional data is essential task in data science and machine learning. The Centroid-encoder method is similar to autoencoder but incorporates label information to keep objects of a class close together in reduced visualization space. CE Centroid-encoder exploits nonlinearity and labels to encode high variance in low dimensions while capturing the global structure of the data. We present detailed analysis of the method using wide variety of datasets and compare it with other supervised dimensionality reduction techniques using NCA, nonlinear NCA, T-distributed NCA, T-distributed MCML, supervised UMAP, supervised PCA, colored maximum variance unfolding, supervised Isomap, parametric embedding, supervised Neighbor Retrieval Visualizer, and multiple relational embedding. We empirically showed that Centroid-encoder outperforms most of these techniques. We also showed that when the data variance is spread across multiple modalities, Centroid-encoder extracts a significant amount of information from the data in a low-dimensional space. This key feature establishes its value to use it as a tool for data visualization. In this paper, we analyze Centroid-encoder and compare its performance with other methods. The article is organized as follows. In section 2, we review related work, and so on and so on. This paper concerns the integration of label information to a nonlinear autoencoder reduction process for purposes of data visualization. Here we develop and comparatively evaluate Centroid-encoder algorithm designed for analysis of label data. While standard autoencoder maps the identity on points, Centroid-encoder maps points to their centroid while passing through a low-dimensional representation. This approach serves to provide a low-dimensional encoding for visualization while ensuring that the elements with the same label retain their class structure. The smoothness of mapping functions ensures that a similar behavior is captured at the centroid bottleneck layer. Conclusion. In this paper, we presented the Centroid-encoder for the task of data visualization when class labels are available. We compared the Centroid-encoder to the state-of-the-art techniques and showed empirically the advantage over other methods. Our examples illustrate that Centroid-encoder captures the topological structure, that is, neighborhoods of the data comparable to methods, but with lower cost and generally better prediction error. These experiments include comparison to the unsupervised Laplacian eigenmaps, UMAP, PT, SNE, autoencoders, the supervised UMAP, SPCA, KSPCA, and as well as MCML and NCA class of algorithms. The algorithms that have the most similar prediction errors when compared to the Centroid-encoder require the computation of distances between all of the points. We demonstrated that the two-dimensional embeddings of Centroid-encoders produce competitive, if not optimal, prediction errors. We also showed empirically that the model globally captures high statistical variance relative to optimal linear transformations, for example, more than PCA. In addition to capturing global topological structure of the data in low dimensions, Centroid-encoder exploits data labels to minimize the within-class variance. This improves the localization of the mapping such that points are mapped more faithfully to their Voronoi regions in low dimensions. Centroid-encoder also provides a mapping model that can be applied to new data without any retraining being necessary. This is in contrast to the several spectral methods described here that require entire training and test sets for computing the embedding encoders. In future, we plan to extend the model in unsupervised and semi-supervised learning. Okay, I hope you got the spice of the paper, spice that must flow. I will go a little bit in more detail right now, so if you'd like, you can stay, but it won't be as organized as it was now. So, introduction. Visualization of data is the process of mapping points in dimensions greater than 3 down or into 2 or 3 dimensions, providing a window into high dimensions so that they can be seen and interpreted. The ability to see high dimensions can assist data explorers in many ways, including the identification of experimental batch effects, data separability, and class structure. Principal component analysis continues to be one of the most widely used methods for data visualization over 100 years after its initial discovery. Nonetheless, PCA often produces ambiguous results, in some cases collapsing distinct classes into overlapping regions in settings where class labels are available. It is tempting to incorrectly infer from this that the data is not separable, even nonlinearly in higher dimensions. Nonlinear extensions to PCA were originally introduced to address the limitation of optimal linear mappings. Also see 7 for additional early references and details. These papers provided first applications of auto-encoder neural networks where datasets are nonlinearly mapped to themselves. This is accomplished first by unfolding them in higher dimensions before passing through bottleneck layer of reduced dimensions, where data visualization is typically done. In the process of nonlinear dimensional reduction, novel latent or hidden features, which are an amalgamation of the observables, may be discovered. A theoretical insight into these algorithms is provided by Whitney's theorem for differential geometry that connects autoencoder to manifold learning. Fundamental innovations were proposed to these ideas in setting of deep networks that made their applications far more effective. The development of tools for data visualization is predicted by design of the objective function and whether it incorporates class label information. That is, it is supervised or unsupervised. The objective function encodes the goals of the dimensionality reduction, that is, what important information about the data is to be captured. This might be a geometric or topological structure as a shape. Neighborhood relationships or descriptive statistics such as class distributions, when class distribution data, when data class labels are available. Alright, I read this one. Unsupervised methods. So principal component analysis is often the first and last tool used for visualization of unlabeled data and is designed to retain as much of statistical variance as possible. PCA, we know PCA, right? Another class of methods used to interpoint distances as a starting point for data reduction and visualization. For example, multi-dimensional scaling is a spectral method that computes point configuration based on computation of eigenvectors of the blade-centered distance matrix. Auto-encoded neural networks. So autoencoder is a dimensional reducer mapping that has been optimized to approximate the identity of the set of training data. Mapping is modeled as a composition of dimensionality reduction mapping G followed by a dimensionality increasing reconstruction mapping H. Okay, let's continue. A probabilistic pretraining approach, known as restricted Boltzmann machine, was introduced in 11 and 10, which initializes the network parameters near to good solution, followed by non-linear refinement to further fine-tune the parameters. This breakthrough opened the window of training neural networks with many hidden layers. Since then, deep networks architecture had been employed to train autoencoders. The pre-training approach was extended further to continuous values, Centroid-encoder. Okay, Centroid-encoder. The autoencoder neural network does not employ any label information related to the classes of data. Here, we propose a form of supervised autoencoder that exploits label information. The Centroid-encoder is trained by mapping data through a neural network with architecture of autoencoder, but the learning target of any point is not actual point, rather the mean of points in the associated class. So Centroid-encoder does not map the identity, now the target points in the image of the map are the so the target points are centroids of the data in the ambient space. And the Centroid-encoder is a non-linear parametric map, which minimizes Within-Christian variance by mapping all the samples of the class category to its centroid. Centroid-encoder backpropagation. Okay, I'm not reading this one. Training algorithm. Okay, algorithm. Input data is labeled data, index of class A, output data, bottleneck layer, output layer. So the nonlinear function is a nesting of function h and g. Result, non-linear embedding of data in m dimensions. Initialization. Calculate the class centroids. Define centroid-based encoder output error. And for k from 1 to the epoch, update theta of the Centroid-encoder. Update parameters theta of Centroid. Well, it didn't say much. I was sort of hoping we will see the loss function somewhere here, but I don't see it. I think that the idea is mostly, I hope I understand the idea mostly. So again, we have this picture of the data set, nicely separated. Basically, training set nicely separated into winner noise cells, and below is the test set, and we can see these are MNIST, by the way, data points, and in the test set we can see that the classes are not distributed exactly in their cells. They are sort of much more spread out, much more sort of noise around. And yes, they have this comparison to the test digits by Laplacian eigenmap. So it's kind of very different. In the Laplacian eigenmap, the sort of these clumps of data points corresponding to certain classes are sort of these narrow bands that are overlapping, while in the case of the visualization of the Centroid-encoder, the data points are more separated into their own, distinct clumps. Also here we have a nonlinear NCN and other dimension TSNE and so on. So I would say that UMAP, I think this UMAP have this unnatural extra clumping of the test points. So they sort of have these very separate clumps of data where you have this mixed class where one of the classes is dominating, but but they have nothing in the middle, right? But in case of the Centroid-encoder, we actually do have some data in the middle, sort of spread out more. So that seems to be giving a better visualization. TSNE, I think, is very similar to UMAP. Basically, very strong clumps, and then you have but you have still something in the middle. But the issue is also that the clumps are too close together. I think UMAP is better than TSNE, but then this Centroid-encoder seems to be even better than UMAP. So classification error of KNN two-dimensional embedded data by different supervised embedding methods or letter, Landsat and volume data. Average misclassification over tenfold cross validation are shown along with standard deviation. Results of methods other than Centroid-encoder, UMAP, SUMAP reported in 40 means. So Centroid-encoder here in the letters seem to be losing. It seems to be just behind this SNRV method, but very close. In the Landsat data, the Centroid-encoder is winning in this metric. On FEMIM data, the Centroid-encoder is winning again. If you look at the Landsat data, we can see that the test data is indeed nicely falling. Majority of data points into the Warner cells. Okay. So okay, thank you very much. I will read the conclusion again. In this paper, we presented Centroid-encoder for text visualization when the classes labels are available. We compared CE to the state-of-the-art technique and showed empirically the advantages over other methods. Our examples illustrate CE captures the topological construction neighborhoods of data comparable to methods, but with the lower cost and generally better prediction error. These experiments include comparison to the unsupervised Laplacian EGMS, UMAP, PT, SNE, autoencoder, supervised UMAP, so on and so on. The algorithms have the most similar prediction errors when compared to CE require the computation distinction of all pairs of points. It demonstrated that two-dimensional embedding of Centroid-encoder produces competitive, if not optimal, prediction errors. We also showed that empirically that the model globally captures high statistical variance relative to the optimal linear transformations, that is, more than PCA. In addition to capturing the global topological structure of the data in low dimensions, CE exploits data labels to minimize the within-class variance. This improves localization of the mapping such that points are mapped more faithfully to their Voronoi regions in low dimension. CE also provides mapping model that can be applied to the new data without any retraining being necessary. This is in contrast to the spectral methods described here that require entire training and testing set for computing the embedding eigenvectors. In future, we plan to extend model in unsupervised and semi-supervised learning. Okay, thank you very much. Again, unsubscribe and dislike. And you made it to the end. I hope to see